channel Mining Engineering. This is the second lecture on the topic Geographic Information System. In the previous lecture, the lecture 1, we have discussed the importance of spatial information and introduction to maps. In this chapter, let us discuss geographic coordinate system. This geographic coordinate system is required to uniquely define location on the Earth's surface. Considering Earth as a round, a system of graticules was developed to locate the position on the surface of the Earth. These graticules consist of a grid of intersecting meridians, that is longitude, and parallels, that is latitude. You can visualize in this picture, this is our Earth, and these vertical lines are the meridians, that is called the longitude, and these horizontal parallel lines are the latitudes. So what are the important graticules? The first one is the equator, then prime meridian, Tropic of Cancer, Tropic of Capricorn, Arctic circles, then North Pole and South Pole, and great circles. Please have a look at the definition and utility of these graticules. Then let us understand the shape of the Earth. There are two types of model. One is a spherical model. In the spherical model, the Earth is considered as a pure sphere, and in the ellipsoid model, the Earth is considered a little bit ellipsoid. Here, the equatorial radius in the spherical model is this much, and in the ellipsoid model, little bit flattening was done in the minor axis. The Earth has a geoid. That is, what is the geoid model? Earth is irregular in shape and is best represented by a geoid. We know our Earth is not a pure sphere. It is irregular. Like we can see, there is some mountains, there is some river area. So it is not a pure sphere. It is not a pure ellipsoid. It is a irregular in shape. It is an irregular area, and that is to describe that irregularities, the Earth is considered as a geoid model. Earth is irregular in shape and is best represented by a geoid. The geoid is the layer of equipotential surface of the Earth's gravity field, which is approximately same as the mean sea level. Variation in heights of geoid's surface is due to anomalous density distribution within the Earth. Earth's topography varies above and below the geoid, that is the mean sea level (MSL). If the terrain falls below the geoid, it represents an ocean, and if rises above the geoid, it represents land or mountain. That you can visualize in this figure. This is the mountain area and this is the ocean area. And this is the geoid, that is the mean sea level. And if the surface of the earth, that is above this geoid, above this MSL, that is that part is represented as the land or mountain area, and the area which falls below the MSL, that is called the ocean area. Describing location, that is a datum. Geoid is a complex surface to be modeled mathematically, hence a best fit ellipsoid is used to measure the latitude and longitude. So if you have to describe something mathematically, irregular shape, it is very difficult to describe. That's why a best fit ellipsoid is used to describe the Earth mathematically. This ellipsoid, along with its point of origin and orientation, provides a frame of reference for measuring locations on the surface of the Earth and is known as datum. The geoid differs from the shape of ellipsoid by plus minus 100 meter. Large number of datums are in use. Most of them are optimized for use in one particular part of the world. Types of datum: local geodetic datum and global geocentric datum. In the local geodetic datum, the geoid is approximately fit at a particular part of the earth like this. Fits this part of the earth well. To describe this part of the area, and this part of area is poorly describing or the earth, that is called the local geodetic system. For this local area, to describe this local geodetic system datum is used, and in this global geocentric datum, ellipsoid or spheroid is a best fit to the earth as a whole. Difference in location: if we change the ellipsoid, the location values on the surface of the earth at any point will also change. Hence, it is very important to keep track of datum while dealing with maps. Most commonly encountered ellipsoid: first one is the Everest Sarjas 1830, one of the earliest spheroid in India. Then Clark 1886 for North America. GRS 80 Geodetic Reference System 1980, current North America mapping. Next one is WGS 84 World Geodetic Survey 1984, current global choice, that's a GPS. And another one is the PG 90 vertical location. For defining a location in 3 dimensions, the elevation values is also required in conjunction with latitude and longitude. Elevation of any point on Earth's surface is measured with respect to the geoid. Traditional surveying uses leveling to measure elevations relative to MSL. GPS treats Earth as an ellipsoid (WGS 1984), hence its elevation is relative to ellipsoid. Some examples of geoid: Earth gravitational model (EGM) and Geoid 99. So this is our Earth surface, our troposurface, and this is the mean sea level or the geoid, which is describing our Earth. And for mathematically represent this geoid, this ellipsoid model is used, and this orange line is the ellipsoid. This is the end of lecture 2.